TSMC has just announced 1.6 nanometer technology. In this video, I will explain how these new transistors work and why from this moment on we have to use both sides of the wafer and why it is huge for the industry. Let me explain. Almost all of the world's chip supply today, about 90% of it, comes from TSMC fabs. And it powers technological progress as well as AI boom. TSMC started making 3-micron technology in 1987. And just imagine, 3 micron is like 3000 nanometers. And just some days ago, they've announced new technology that can enable chips at 1.6 nanometers. Now, these new transistors involve two big innovations. First of all, a novel transistor architecture and backside power delivery. And this is something that has never happened before, a separation of power interconnect from the signaling. And as a chip designer, I can tell you it's a big deal for the entire industry.
12. This is a Mona Lisa. No. This is a Rembrandt. No. I think it's a Michelangelo, right? Sculpted in silicon.
But to understand the complete picture, we have to start with transistors first. All modern chips are made up of transistors, these tiny electrical switches that can be turned on and off. This is what a classical planar transistor looks like. This switch is controlled by the gate, and when we apply a certain voltage, or more specifically a certain electric field to the gate, it opens the gate, and the current flows from the source to the drain. As planar transistors were scaled down, we shrunk the size of the transistor, the size of the channel. And here we faced many problems, and excessive leakage current is just one of them. And eventually the solution was to completely change the transistor structure. So they took a planar transistor and stretched the channel up as a vertical fin. While in a planar transistor, the conductive channel is only on the surface, with FinFET we have a conductive channel on 3 sides, while the gate is wrapped around it, allowing us to better control it. And of course, compared to the planar transistors, FinFET transistors are much more compact, so with that we're able to pack much more of them into the same silicon die. The first commercial FinFET devices were introduced by Intel in 2011, when I was still at university. And wow, we're gonna talk a lot about the competition between TSMC and Intel today, because it's really heating up. So a few years after the first Intel's FinFET device, Samsung and TSMC started fabricating 16 nanometer and 14 nanometer FinFET chips. And since then, TSMC has led the evolution of FinFET. Nowadays, all the cutting-edge chips are built with FinFET. However, FinFET technology has already reached its limits in terms of how much we can squeeze it in, how much the fin can go up, and how many fins we can place in parallel, side by side. And again, huge leakage became a problem here. So to further shrink the transistors and drive down the costs, the whole industry is now moving towards the new gate-all-around transistors. I've talked about this technology for maybe some years now, but now it's finally moving to mass production. TSMC calls their gate-all-around transistors nanosheet transistors, but basically it's the same thing, just a different name. TSMC plans to begin the production of gate-all-around transistors in the beginning of 2025, with the first ones to appear in iPhones. Now, how does a gate-all-around transistor actually work? Basically, they took the FinFET structure and turned it horizontally, placing several of these sheets on top of each other so that we can multiply the number of fins vertically. And the best part about it, that now the gate is completely wrapped around the channel. The biggest gain with this technology is in power efficiency. Gate-all-around transistors consume up to 35% less power compared to FinFET technology. Now, just a few days ago, TSMC debuted A16 technology on their roadmap, where A stands for angstrom, and as we discussed in the previous videos, this has nothing to do with the real dimensions in the chip itself. And now we are coming to the most interesting part. So TSMC's A16 technology will be based on gate-all-around or so-called nanosheets transistors with one very interesting twist: backside power delivery. And this is really groundbreaking. And yes, Intel is doing kind of the same thing, and we also will talk about this later in the video. But now let's understand what is this backside power delivery and why it's so crucial. Ever since Robert Noyce made the first integrated circuit, everything has been located on the top, on the front side of the wafer, with all the signal interconnect and power delivery coming from the front side. So this backside power delivery is quite a huge change, because we will move all the power lines, so power mesh, underneath the substrate to free additional space for the signal routing on top. You know, when it comes to modern chips, there are billions and billions of transistors that are interconnect with each other. And there are many levels of signal interconnect coming on top of the transistors. And then there is also a power mesh, power network on the top. You can imagine it as a network of power and ground lines that distribute power across a semiconductor chip and provides the power supply to transistors. Now imagine if we can move all this power to the backside of the wafer. This will reduce the complexity of the wiring interconnect a lot, letting us to place and route transistors much more densely, so closer to each other, and also reduce the congestion problems. And of course, this concept of separating power from the signal will give much more freedom to the EDA, electronic design automation tools, which are used at this stage. And this means this change will affect not only the manufacturing flow, but also the chip design flow itself. And this will require a lot of learning from our side when it comes to power mesh and the heat distribution on the chip, for example. TSMC will start producing chips based on N2P and A16 technology, which is its version with the backside power delivery, in 2026. So I'm really looking forward to see how it goes. And as mentioned, TSMC is not the only company working on this innovation. Intel is doing the same thing. Actually, Intel wants to be the first, even ahead of TSMC, to bring the new transistor technology and power delivery tech into production. But before we talk about Intel's strategy and associated costs and risks, did you know that the advanced gate-all-around and FinFET transistor architectures would not have been possible without ASM's equipment and process technology? The process of building the most advanced silicon chips nowadays includes thousands of steps, and the most critical among them are lithography, etching, and deposition, because these are repeated over and over again as transistors are being built on top of the wafer. As we scale transistors down, we need to deposit even thinner layers, and very precise deposition techniques like atomic layer deposition are essential here. Atomic layer deposition is a special technique that allows to deposit different materials on the wafer atom by atom. And with that, we can evenly build very thin layers that are just one atom thick. Can you imagine that? And to do that, the most advanced semiconductor fabs like TSMC and Intel use atomic layer deposition machines from ASM. And I'm very excited that ASM is sponsoring this part of the video. ASM is a Dutch semiconductor equipment manufacturing company, and they are one of the pioneers of ALD technology, with a 55% global market share in this sector. They definitely deserve credit for their contribution into the continuation of Moore's law, because without their machines, the advanced FinFET and gate-all-around architectures would not have been possible. And of course, in the future, when the next transistor architecture, so-called CFET architecture, will become commercially available. And this will clearly stimulate the demand for the ALD equipment from ASM even more. You can learn more about ASM and their products through the link below. Thank you, ASM, for sponsoring this video. Now, I want to spend some time talking about Intel's ambitions because there are some very interesting aspects to this story. As you may know, for the last 5 years, Intel has lagged behind Samsung and TSMC in the advanced chip manufacturing. But now, this is their chance. This is their moonshot to be the first, even ahead of TSMC, to bring the new transistor architecture and power delivery into production. For Intel, gate-all-around technology is coming together with their backside power delivery in the 20A process node. And don't get confused with the terminology because each fab has its own name for gate-all-around. Intel calls it ribbon fat, but it's kind of the same thing. And now they're putting the final touches on it. And this 20A node we have to watch because it's gonna be very important for Intel. And I personally think it's a super risky move for Intel to introduce two innovations at once, because you typically want to introduce it one by one to understand where the problems are coming from. But introducing two technologies at once is clearly Intel going all in. And I see a lot of risk here because, probabilities multiply. Let me know what you think in the comments. And what's so interesting that in the past, Intel used to be the conservative one and TSMC was risky. But this time, it's completely the other way around.
We also announced that we're going to get 5 nodes in 4 years. We're going to do something unheard of in the industry to return Intel to process technology leadership. And while we're not finished today, we see the end is soon in front of us on that journey. And Intel 7, shipping and ramping in volume. Intel 4 with our Core Ultra launch, shipping and ramping in volume. Intel 3 is production certified and will be with our server products launching in the first half of the year, going into volume production. So with this, we've gone on an incredible journey, but then it continues into what we call the Angstrom era. And for this, Intel 20A and Intel 18A, the adoption of ribbon-fed, a new transistor structure, of power via power delivery technology.
But this time, they really have to deliver. Air Lake will be the first Intel CPU to feature first ribbon-fed transistors and backside power delivery, which Intel calls power via. And as we just discussed before, the idea is the same. The power will be placed under transistors on the backside of the wafer. This is all cool, but let's be honest, from the entire Intel's roadmap, the most interesting node is 14A, because this is gonna be the most pivotal moment for the Intel Foundry. To remind you, it's planned for 2027, and I'm really curious to see how it goes for Intel, because it involves one huge update to the flow. One huge and very expensive elephant in the room. 14A will be the first process node where Intel is planning on using the new high numerical aperture EUV lithography machine from ASML. One of these reportedly costs about $380 million, and this comes with a lot of risks. Apart of the risks associated with the adoption of the new tooling and the updates required to the flow, the second risk is economics, which haven't worked so far. The reason why Intel is switching to this machine is that it will allow them to print even finer transistor features. EUV lithography machines can print lines of up to 13 nanometers in width. At advanced nodes beyond 3 nanometers, traditional EUV lithography machines will reach its limit, and it will require chip makers to move to EUV multi-patterning. And this is complex and expensive. And that's, by the way, how TSMC is planning on achieving N2 and N1.6 nodes. Multi-patterning is a technique which often used to overcome the limitations of what is possible with lithography. I've talked about it in the video about the Chinese chips. It involves several layers of masking and several wafer exposures to pattern a single transistor feature. And these new machines can enable resolutions up to 8 nanometers, and with that enable more advanced process nodes. And Intel will be the first fab to adopt these new EUV machines in their flow. Now, when we talk about how chip economics work, and by the way, it's a super interesting topic and I want to make a separate video about it. If you don't want to miss it, subscribe to the channel. According to Moore's law, the number of transistors on an integrated circuit roughly doubles every 2 years. And many people misunderstand this law and think that it's just about a transistor size or the density, but it's actually about the economics. It's about transistors getting cheaper and cheaper. So now, when we consider the competition between TSMC and Intel, the clash of two giants, it comes down to just one simple question. Who can produce it first at decent yield and the most important at the minimum cost? And here they not only have the pressure of time, but also the cost pressure. And so far, considering the costs of the new EUV tools and the process adaptation and flow adaptation required, it turns out that high-NA EUV machines are simply not economically viable, as the price per wafer in this case will be simply too high. And according to TSMC, that's why they are passing on this machine for now. I was reading another day that the reason why the price per wafer appears to be too high, because at the moment the lithography process with this new machine takes more time per wafer. And this means the fab can process less wafer per day, and this limiting the fab throughput and of course driving up the costs. To make economics to work, Intel must get creative here, and it seems they have some ideas how to get around this and make it faster and cheaper. Their intention is to use direct self-assembly, and this is a very complex process, and to be honest, I don't understand it fully because there is a lot of very complex chemistry involved. The idea is that you cover the wafer with a special polymaterial and then bake it for an hour or so. And when it's baked, these polymer materials self-organize themselves into tiny lines. And according to some research, which was previously done on this, we can use high-NA EUV machines to help to guide the way it's organized on the wafer. But the main problem is this approach was in the research phase for a decade or so, and it wasn't adapted because the defect rate was just too high. But I'm really rooting for Intel here because for everything they did for the industry, I really want them to make it to work, you know? But by now you're already aware of all the different innovations Intel is trying to pull together at once over the next couple of years and how high the risks are. But if they manage to make it to work, especially the 14A node, this will be the pivotal moment in the history of Intel. And this will surely help their stock to recover. This video is already getting quite long, but just a couple of words what is coming on next. Following high-NA EUV machines, we will eventually get to the hyper-NA EUV machines. Let me know if you want a video about this one in the comments. After gate-all-around architecture, all the fabs will be moving to the next transistor architecture, so-called CFET, complementary FET transistor. And this one will help us to further reduce the footprint. And I truly believe in the vertical future of transistors. The idea of CFET is to fold two nanosheet transistors on top of each other vertically to build a CFET structure. Intel was the first company back in 2020 to make a CFET work, stacking NMOS transistor on top of PMOS. In this way, they built the simplest logic circuit you can imagine, a CFET inverter. When input is applied to such a circuit, its output is a logical inversion of the input. So if we have 1 at the input, we get 0 at the output, and the other way around. And a funny fact that already back then, they had to use the backside power delivery here. And the reason is that when we stack devices, the complexity of the interconnect on top just explodes. So it's clear that vertical transistors together with the backside power delivery is the future of transistors and the future of silicon chips. I hope you enjoyed this episode, and if you loved it, please share this video with your friends, colleagues, and on social media. I see all your reposts and I really appreciate it. And let's connect on LinkedIn. There will be some serious changes in my career, so if you want to know, let's connect on LinkedIn. You can do that by scanning the code here. Thank you so much for watching, guys. I wish you a beautiful day and see you in the next episode. Ciao.